So in our last video, we established these two derivatives, that the derivative of sine of x is cosine of x, and that the derivative of cosine of x is negative sine of x. Let's build on this and come up with the derivatives of some of our other functions. So let's try to calculate the derivative of tangent of x. So if we stop and think about this, we can write this, and I'll use the notation. So tangent of x, and I'm going to just use this prime notation, is going to be what sine of x over cosine of x prime is going to be. So if we stop and think about this, we can figure this out using the quotient rule that we have established previously. So we're going to take the bottom function, cosine of x, times the derivative of the top function. So, and I'll write it out in steps here. So sine of x prime minus the top function times the derivative of the bottom function, so derivative cosine of x prime here. And then we're going to have the square of the function on the bottom. So as we write this out, so the derivative of sine of x is cosine of x. So we have cosine of x times cosine of x. And then we're going to have minus sine of x times negative sine of x when we take the derivative of cosine. And then we're going to write this as cosine squared of x. And from there, we get that this is then cosine squared of x. And then we have sine times sine, so that's sine squared. And we have a minus and a minus, so this becomes a plus sine squared of x all over cosine squared of x. And then if we remember our trig, we remember that this cosine squared plus sine squared is just equal to 1. So what we get is 1 over cosine squared of x. And the succinct way to write that would just be secant squared of x. So what we have for the derivative of tangent is just going to be secant squared of x. Now, if we go ahead and did something similar using the product and quotient rules for the other trig functions that we're used to seeing, so the derivative of secant of x, which is 1 over cosine, what we get is secant of x tangent of x when we do that one. And if we do cosecant of x, the derivative of that function is negative cosecant of x times cotangent of x. And the last function that we would need to write about would be the cotangent of x. And when we do that, we get negative cosecant squared of x. Now, for the most part, you can, as long as you remember the sine and the cosine derivatives, and you are comfortable using the quotient rule, you can derive all of these derivatives again in the same way that we just derived them up here. But they may be worth your time to remember, to just memorize these. In particular, I would say the tangent and secant ones will come up more often. So those might be worth your time to remember memorizing, if not all of them. So let's find the equation of the tangent line to y equals e to the x times tangent of x plus x at 0, 0. So if we go ahead and try to do this, we first need to find the derivative. So y prime here. So what we have to do is we have to do e to the x times tangent of x, and we need to find the derivative of that. And we need to add that to the derivative of x. So for this first bit, we actually have to use the product rule. So remember, we'll take the derivative of the first thing, so e to the x has its own derivative, and leave the second bit alone, so tangent of x. And then we leave the first thing alone and take the derivative of the second. So the derivative of tangent we just saw is secant squared of x. So we get this for that first derivative here, and then the derivative of x is just 1. So we get this value here. So now we want to know the derivative value at 0, so we just plug in 0 here. So at 0, y prime equals e to the 0 times tangent of 0 plus e to the 0 times secant squared of 0 plus 1. And we get 1 times 0 plus 1 times 1 plus 1 here. So the derivative at this point is just 2. So if we want to come up with our tangent line using point slope form, we would get that it should just be y equals 2x. So let's go ahead and look at a graph and confirm that. And when we graph both functions, we see that we do intersect where we say, and our slope of our line, y equals 2x, appears to be just about right.